Today we will cover the torsion theory, and next week probably we will study on beam theory. Torsion theory and beam theory are two most important subjects in solid mechanics. And as I emphasized in the very beginning of this course, the most of the structure we will deal in this course is the one-dimensional structures. So we started with a bar, which is subject to a longitudinal force, and which is simply axial load, either tension or compression. We drive the equation to calculate a deflection, right? Deflection or stress, which was a bar. And now second structure is a shaft. Shaft is subject to a torque. And so today we will define what is torque and what is the shaft. And we will mostly focusing on a circular shaft, okay? A shaft with a circular cross-section. And other shaft with a different general shaped will require a lot of theoretical derivations. So we will just avoid that complications. We will just focus on circular cross shaft, either solid shaft or thin wall shaft. So anyhow, once you understand the how to calculate the stress and what's the deformation in a shaft with a cross section, I think that will be quite enough for you to understand torsion theory and apply it to a real structure. Again, the torsion together with the beam theories is very critical issues in understanding the structures. It's not just a slender structure. The torsion theory, understanding torsion theory will be very useful when you design many kinds of structure. For instance, before I go to in detail about the torsion theory, I'd like to where is well, wind turbine blade. Well, I will just pick any. Well, these days, I'm sure you heard about many times about the wind turbine blade, wind turbine energy, and which, for instance, well, these wind energies can be converted into electric energy by using this blade. When wind blow into this blade, then the blade will certainly rotate, and that rotation will rotate a generator behind it, and that generator will generate electricity. principle is very simple, but the size is really, really large. This length, guess how long this length is? This length is 50 meter or 60 meter. So diameter is about more than 100 meter. So huge. It's much larger than an airplane. And imagine how heavy it is. The weight of each blade is about 20 or 30 tons, each blade. And totally about 50 or 60 tons. And this tower should support, strong enough to support the whole blade together with the nacelle, which has all the electricity, motors and generators and gears and so on. The reason I'm introducing this, I'm remind you of this blade is that when wind apply force to this blade not only subject to, of course, this is the blade subject to a wind force, and this blade will bend like that. Of course, it will rotate, but it, of course, is bend like that. That bending bending behavior will be covered next week. But not only bending, but also it is subject to a torque like that. When wind applied to the surface will be subject to a torsion. So this blade will subject to a lot of torsions, and you need to understand how to design and how to calculate the stress and angle of rotations by understanding this torsion theory. Well, there are a lot of interesting story or design methods is needed in design process. Actually, last 2 weeks, I went to European wind turbine companies. One of them were Vestas. Vestas is one of the top companies in all over the world, and which is located in Denmark. And they design, their market share is more than 20 or 30%, and one of the biggest company. And the other company is the Siemens. Siemens is supposed to be a German company, but the factory was located in Denmark as well. So anyhow, they have their own design, and the designer should understand this torsion theory to better design their blade. Again, this is the not short, it is the 60 meter long. It's a huge structures. And see, blade is cross-sectional blade is like that, and this is the chord length. And wind is supposed to have in this certain direction. This is the called angle of attack. Okay, I'm sure we will study a little bit about this wing theory in fluid mechanics, and the load is supposed to toward this wing with the angle alpha with respect to this chord length, and these all, and here we usually have, this is the force called dragging force, and this is the force, vertical force will be a lifting force. So when we have a wing and there's a wind distraction, that this wing will automatically lift by this lifting force. Of course, there is the dragging force, which is also because of this wind. So anyhow, this makes a plane like that. When you rotate, it makes a rotation like that. So this is the plane of rotation, and the resultant will have not this much, a little bit of this way, such that this one has a resultant, component in plane of rotation. This force will rotate this wing. So anyhow, there is a center called a shear center, and this force is passing through this little. This is the aerodynamic center, and this center and this center is different. What is the shear center? And if all the forces is passing through this shear center, there will be no torque, no twisting torque. But since this point, two different points, and this distance times this force is causing some twisting moment. Well, it is a little bit complicated here, but I just want to emphasize that this even simple blade is subject to a lot of torque, and you better understand a torsion theory well to even design the blade for wind turbine generator. Okay, so let's define a shaft. Again, shaft is subject to a torque. Okay, this is the torque, or sometimes it is called torsion. Meaning is same. A one-dimensional structure transmit torque is called a shaft. A shaft can have a very different types of cross section. Okay, and this shaft can be of course curved, but let's just focus on a straight shaft. And again, this is the subject to a torque. And in this chapter, we will start the stresses and strains of a shaft resulting from a torque. Okay, that is the shaft. And different types of shaft. It shows the many different types of cross sections. First one, of course, it has the circular. We are using a terminology saying solid. Solid means it is a field. Okay, it's a field. It is called a solid, and sometimes we use the terminology saying hollow. Means that there is empty inside. Solid, hollow, and this one is the closed. And sometimes we're saying open. Means that this one is the closed. Okay, this one is closed. A line along this surface is closed like that, and sometimes we have open. We have a slot like that, then we call open section and closed section. Well, for the solid, we cannot say either closed or open. It is just a non-circular solid shaft, and this is the hollow circular shaft. And the theories we will cover will apply to these two shafts, and for the thin wall cross section. So we will cover this and this one. And the other non-circular shaft, like rectangular, requires a lot of complicated theoretical derivation, and so we will not cover this one. And thin wall open section also a little different subject. So anyhow, we need to understand solid, hollow, or closed, or open. That differentiates between different types of shaft. Okay. Okay, you gotta remember that solid, hollow, and closed and open. Now let's focus on solid circular cross section. Deformation of a shaft with a circular cross section. Actually, this deformation can be equally applied to a circular hollow shaft. Can be either solid or hollow. Can be a solid or hollow shaft. And at the very beginning, in studying bar, we started with a deformation first. We observed the deformations, and deformation is proportional to a length, inversely proportional to area, and inversely proportional to Young's modulus. And similarly here, we observe the deformations of this solid circular shaft subject to a torque. Okay, this is the before deformation. Before deformation. Okay, this is let's say we mark a 4-point A, B, C, D, and we just connect them. We simply, this is the just arbitrary point and arbitrary lines, and indicating some reference lines. Okay, reference lines. This is the before deformation, and after deformations, we apply torque. After deformation means that we apply a torque T with respect to this plane, bottom plane, meaning that we fixed at the bottom. We fixed at the bottom, and we observe the deformations. And this vertical along the shaft, the coordinate system we call Z, okay, Z coordinate, and simply the A point moves into a different position, A prime. And other point, B and C, since it is fixed, and B and C is the also fixed, and D is also stationary. So only A moves toward A prime. And imagine that any point here or here, it moves into different positions, and this makes new positions make a straight line. Okay, this is the deformation observation, and is very important. It seems to be very simple, but this will be the basis, starting point toward all the theory, all the torsion theory. Then what we will study here is that how much we will have rotations under torque T with given length and given diameter and given material properties. Material properties and geometries and forces, all combine them, and which will give us the amount of rotation and amount of stress. The stress resultant stress should be equal to a torque T. Okay, now displacement field in a shaft, which you just observed, and this is the top side. A moves to A prime, and any point here, E, also moves here. And remember, we have the shaft like that, and it also moves like that. But on the surface, cross-section, any point on cross-section is also moving toward in theta directions. And let's say this is the angle phi, and this is the radius r, indicating this point E. Okay, indicating point E. So E is the radius, has a radius r and angle phi. I mean, phi is the amount of rotations. And simply the U, let's say this is the hoop direction, theta directional displacement is simply r times phi. Okay, r times phi. And this phi, okay, this phi, let's take a look at the different sections. Let's say these sections or this section. If we look at this phi is gradually increasing, right? So phi is the gradually increasing, proportional to axial length, right? At the bottom, if we go z equals 0, there will be no rotational angle, and phi is certainly proportional to this z. So, okay, r times phi is hoop theta directional displacement, and phi is certainly proportional to z. Now, which means that we simply combine these two equations, and theta is proportional to r and z. Theta displacement at any point is proportional to r and z. Okay, these C we don't know yet. The proportional coefficient C, which we don't know yet, but what we know is that hoop directional displacement is proportional to r and z, which is very important observation from this displacement field. Well, in fact, any point can have three component of displacement in polar coordinate. This is the polar coordinate, not XYZ Cartesian coordinate, polar coordinate. This is the Z, this is the theta, and this is the R. Three displacement field. Any point can have X, Y, Z. This is the polar coordinate, so R, theta, Z. And what we observed here is the U theta equal R and proportional to R and Z. That's what we observed from this displacement. And simply, there is no displacement in Z directions. And there is no displacement in R direction. Okay? This is a critical point starting toward the next step. Okay, any point in shaft can have a three component displacement. Well, not just for the shaft. All kinds of material bodies can have a three-dimensional displacement, three component, right, in three-dimensional space. And here, shaft can have also a three-dimensional, three component of displacement, R, Z, theta. And R, there's no R directional displacement. Why? Well, we cannot conclude that at this point, but just say this is observations. And when we rotate a shaft, the diameter does not get larger or smaller. Okay, when we rotate the shaft, the diameter is remains the same. That means the R is 0. Okay, UR is simply 0. And when we rotate the shaft, the length does not expand or contract. It just length is the remain also the same. That means in Z direction there is no displacement. Only displacement that we observe is that theta directional displacement, and which is proportional to R and Z. Okay? So this is the mathematical expression for this kind of displacement, geometrical displacement. Okay? Very important. Once we understand, we have the displacement in terms of the coordinate system, next step is straightforward, meaning that we have strain displacement relations. So using this displacement, we are able to get strains, and also we have a strain stress relation, which is material properties. So we can move to a stress, and stress will be caused by this torsion. So the stress will be given in terms of stress. And so finally back to here, this C will be determined. Okay? This step is very important. Okay, you need to, okay, this is the displacement. What will be the next step? Strain displacement relations. Displacement will be put here, and next step is what? Stress, strain. Displacement will be here, and strain will be here. And stress, next step is torque, and stress will be here. So torque is a given value, it's a known value. And so given torque, we will have stress and strain and displacement. Finally, what will end up with is that this C will be given in terms of T. Okay, then it gives us all the information we need: strain, stress, and displacement, and so on. This procedure is not just for the shaft. This procedure is actually also equally applied to a bar, this shaft, and beam. All these structures is this step: displacement, strain, stress, and external force. Okay, keep that in mind, those procedure, okay? And this is the, we have only theta directional displacement, and R and Z displacement are 0. And this is the, again, just a remind. Well, this is the same as this one. So this one and two components are 0. Now, strain displacement relations. And do you remember that epsilon xx equal ux and epsilon yy equal uy? And this do you remember these relations? Epsilon xy is the half ux y plus u y x. Right? You remember this equation?
No.
What? 요거? It's just a proportional constant, which is unknown. Proportional constant. You understand? Proportional constant. Constant, we don't know yet. Okay, we don't know yet, which will be given in terms of a torque.
See, number or equation.
A constant. Constant. Number. Before you guys come to class, you gotta read something. What you will study. Okay. Okay. Anyhow, C is the constant, and that will be given in terms of applied torque T.
And displacement line not curved in a line.
No, it will be just a straight.
Straight.
And yes, it's a straight. And that's why we have the U theta is the proportional Z and R. Okay, why? Okay, that's very good question. Why is not the curve? I mean, it can be, you may imagine that this one can be this way or this way, right? That can be, I mean, you can possibly assume that. But if you have this kind of, why it should be a straight line? Why it should be a straight line? Well, if it is the curved, well, this story will be a little bit long, but this one, let's say this is the curved like that, then all the element should curved like that, right? But that contradict comparability. This has to be straight to have every portions have an equal displacement. If it has a band like that, then there won't be no comparability between each part. Okay, back to this strain displacement relations. Okay, this strain displacement relations. Okay, I'm sure we covered this subject, right? And exx is given ux derivative with respect to x, right? And epsilon yy is the y directional displacement with respect to y. And epsilon xy is the yxxy. Okay? Again, this is the relations between displacement and strain. How many components, strain component do we have? We have 6 components of strain. And how many stress component, displacement component do we have? We have only 3. ux and uy and uz. Only 3 component of displacement. So I will remind you again that epsilon xx is the x, and similar to this one, this can be defined, for instance, uz, z, okay? And this one is simply y. Well, what does it mean? This means, let's say we have a rectangular cross-section like that, and if we extend this much, okay, this much, is simply L, this is L over delta. That is the axial strain, right? Delta is a relative displacement, and x is the L. Delta over L is the simply a simple version of this derivative. X, y, and zz. And how about the shear terms? Well, as defined here, the angle epsilon xy is the average of the theta 1 and theta 2. That is the what? Shear strain. And shear strain is always related to a change of angles, not lengths. Right? So this one, theta 1, what is the theta 1? Theta 1 is simply a y-directional displacement. Y-directional displacement changing with respect to x. Pay attention. Y displacement with respect to x is the theta. And how about this one? This is the x-directional displacement with respect to what? Y. So adding those two terms will give us this epsilon xy. Okay? Similar to this one, we can define this and this, all the shear, 3 components of a shear strain. Okay? So what is called? This is called strain displacement relations. Once you have the displacement, you will have the strains easily using these relations. Okay, this is the strain displacement relations. Back to here, and we have this strain. I'm sorry, we have the displacement like that, but only difference is that this is in polar coordinate, not the Cartesian coordinate. So anyhow, let's say epsilon zz, epsilon rr, epsilon theta, and zz is simply uz, derivative with respect to z. And what is uz? 0, right? And theta, with respect to theta, there is no theta there, right? So will be 0. And rr, ur is 0, right? So simply all normal strain, diagonal terms are 0. And epsilon r theta is also 0. Why? This associated with r and theta plus and theta r half u r u 0. And how about theta? Theta we well, there is the this is not the exact equation in polar coordinate system. We do have a little bit of a different equations, and okay, let's find out that equation. That is the only difference between Cartesian and polar coordinate. Well, again, this is the Cartesian coordinate, epsilon x 1, 1, or 2, 2, and 3, 3, and simply displacement with respect to the same coordinate, and the shear strain is simply adding those two angles, and those are all Cartesian coordinates, okay, Cartesians, but in polar coordinate system, the component is a little different. The reason is that the angle is changing. Anyhow, the conclude, what I want to say is that this one is the also 0. Okay, this is also 0, and the epsilon z theta is the also z theta is the only non-zero component, and which is the theta z and z r round theta. The reason is that I forgot. There is some terms here. Okay, that's my what I was trying to find the equations. And there must be some terms here. So this one, I'm sure, will be 0. And these terms, and this is the only non-zero terms. As you can see here, u theta has the function of z there. So with respect to z, this term will be CR, and this term z is a 0 displacement, and this term will be this up here. So only we have these terms, CR. What about the last one? RZ, right? RZ is the UR equals 0, UZ equals 0, so this will be certainly 0. So point is that, conclusion is that this is the displacement. You know, that shaft and the line is moving like that. This is the equations representing that deformation field. And this is the strain. All zeros, only non-zero is the sigma epsilon z theta. Z theta. Z theta, what does it mean? Z theta. Let's say we have, this is the z theta. Z theta means that this is the z, this is the z, and this is what? Theta. And this is the plane. Theta and z, there is the this rectangular shape, and this will have the deformation like that. And it has, as you can see, this is the angle there. this is the shear strain component epsilon z theta. Okay, z theta. This angle is simply changing. This is the only one strain, non-zero strain component. So anyhow, here, as you can see here, from this relation, we have a C times R. Again, C is just constant. And this gamma z theta is simply 2 times of epsilon z theta. And gamma z theta is here. And another very important observation here is that imagine this is the dz and this is the d phi, okay, and this distance, so from here to here is the r. So this dz, this is the dz. This movement can be represented by 2 ways. One is this times this length times this angle give us this one. At the same time, this r times d phi will give this displacement. So what dz times this angle gamma z theta should be same as what? R times d phi. So what gamma z theta is simply d phi over dz times r. Remember that gamma z theta is given as a what? C times r. Do you remember that? Right? C times r. Now, what is the C? d phi dz. What does it mean? d phi dz. The angle of rotation with respect to unit length. Right? Angle of rotations for the unit length is simply, let's say, this is the rotate phi. The bottom part is fixed. And this length is the L. Then d phi dz is simply, let's say, phi 0 over L. Okay? Total, this is the relations. d phi dz is simply unit angle of twist corresponding to a unit length. That is the C. Okay, that is the C, as you can see here. So anyhow, normal C, we just came to these relations. Gamma z theta is given as d phi dz times r. And I think this figure, these relations, is the most critical observations in driving these relations. So anyhow, again here, C, this is the constant. Let me ask, d phi dz or phi 0 over L. That is the amount of rotations of shaft. that amount of rotation will be simply proportional to the torque you apply, right? And simply relate to a material stiffness of this shaft. So that we will drive. Next step is that stress strain relations. Stress is simply sigma z theta equal shear modulus G times epsilon z theta 2 times. So simply G times gamma z theta. Okay, sigma z theta is simply G gamma z theta. We don't have to worry about any other material properties because all the stress component, all other strains are 0 except this gamma z theta. So the only one stress component which is non-zero is sigma z theta. Okay, what is a sigma z theta? Again, if we remember this this one, z theta means that this is the z surface, right? Z and theta and z theta and this one. This is the sigma z theta, or simply we call tau, representing shear stress, z theta. So as you can see here, this on the top surface, we have this tau, okay, tau, and the torque applied should be same as this tau times this area. What is that? R d theta, okay, this, let's say d theta, and R times and dr. This is the what? This is the dA, right? Dr, R d theta is simply this length, and dr times give us this area, right? So this is the integration of R. I mean, tau is the force. Tau times this is the dA, is simply force you apply, right? And how do we calculate the torque? We have to multiply R, right? We have to multiply another R. Tau times dA is the force, and we have to multiply R, giving us torque, right? So simply, that's why we have a tau A dA is torque, and tau, we have a relation tau equal G gamma, and G and gamma is the given as the R times d phi dz, which we obtain here, gamma R times d phi dz, and we insert this phi into here, tau into here. What do we have? G, there was R here, and there was R here. So R square, GR square, and dphi dz, and dA. And dphi dz, we know this is the constant, so we can have this term out of integrations, and G stiffness is also a constant, and we can have integrations out of integrations. And we have the R square and dA, and what is called R square dA. What is called polar moment of inertia. R square dA we call polar moment of inertia. This is the nothing to do with the material properties. This is solely related to a cross-sectional property. Cross-sectional property. Not the material property. Cross-sectional, geometrical properties. And from here, dphi dz is simply T divided by Gi, T divided by Gi, and dphi dz is simply phi over L, and so this is the final equation we have. And if we insert this equation into a tau G dphi dz R, if we simply put into here, then we have tau equal GRT over GIP. So tau is simply given as the torque R, T times R divided by IP, polar moment of inertia. This is the final equation. And let's compare between, okay. I know you guys are a little confused, and so let me drive the equation again. Displacement, strain, stress, and stress and torque. This is the steps we need to follow. Okay, starting from displacement and strain, that give us a simply, displacement is simply, oh man. Displacement and strain. Displacement we observed is that U theta equals simply C times what? R and Z, which represent this kind of displacement. Right? Keep that in mind. That's the first step. Epsilon theta, okay, only we have a theta displacement, right? Others are all zero. There's no R, no Z. Only theta, only hoop directional displacement. So that is the function of R and Z. Why? Because this displacement is simply linearly increasing with respect to Z and linearly increasing R from inside out. right? Okay, that's the displacement. Now, displacement strain relations, we have all other terms is 0 except that epsilon, which component? Z theta. Remember that, this surface, this way, this is the what? Z and theta. So epsilon, Z theta is the only non-zero component, and with respect to this is the half U theta R. There's another term which is 0. So simply what? Gamma Z theta is the twice of epsilon Z theta, right? And which is what? R. Simply Z times R. C times Z, right? That is the strain, shear strain. So this is the starting point, and this is the strain. All other strains are 0. Now, okay, that is the displacement, the strain relations. Now, stress. What is the strain stress relations? Very simply, tau, which is a sigma Z theta, is simply G, material properties, times what? Gamma Z theta. Z theta. And simply tau is G times C times Z. That's the shear stress. Am I right? Right? Okay. This is the first step. This is the second step. What is the third step? Stress and torque. What is the relations? In cross sections, and we apply torque, and this is the tau, and this tau is applied to these sections dA. So integration this tau dA will be force, okay, force, and we need to multiply this R to have torque, right? So if we put this equation into here, and simply what do we have? We have G times C integration R square dA equal T. But this C, what does this C means? This C means that we have the observation that always this figure. This is R, this is a d phi, and this is the this is what? This is the this angle, and this represent this the gamma Z theta, right? This is a shear strain. This is the Z theta. So this is the Z theta, and this is a dz. So dz times this length times gamma Z theta should be R times d phi, because this movement can be represented by this one or this one, which means that gamma Z theta equal R times d phi dz. And simply this is what? Right, this is a C. So anyhow, what is this term called? R square dA. This is the IP, polar moment of inertia. And what is the unknown here? Unknown is a C, which is d phi dz equal T times GIP. That was unknown. Now we have them, express them in terms of torque T. This is known, and G, material property, also known, and IP is the polar moment of inertia, which is also known. So dP dz, twisting rate with respect to z is now can be represented in terms of T, G, IP. Okay? Now we put in this term into back to tau here. Tau. Now tau equal G times T, G, IP, R. So simply T over IP, R. Okay, tau is like that. T over IP times R. And this one, the total phi over L, d phi dz is a twisting rate with respect to z. So can be represent total phi over L. So phi equal TL times GIP. So this will be final and this will be final. Two final equations. Okay? Shear stress distribute over the surface should be T over IP times R, and angle of twist of the shaft with the length L is the TL over GIP. Those two equations are final. And how much you get the angle of twist, how much it deforms, how much stress we will get on the torque. And the shaft material stiffness is a G, and size of the shaft is represented by IP. What is the IP? Okay, let's get back to polar moment of inertia of cross-sectional R can be R square dA. What is that? Do you know? Well, dA is simply R times dr times d phi, right? d theta, right? So R third scale. So 4 over R 0.4 2 theta is 2 times phi. So simply pi over 2 R 4 times. IP is the pi over 2 times R0 at 4 times. Okay? You need to remember this. As you can see here, R, if you increase R twice, IP will be 16 times. Right? That means, if larger shaft will very much effectively decrease shear stress and decrease the angle of twist. Now let's get back to this comparison. Even though we went through a very much complicated procedure for this torsional theory, the final form can be easily compared with those for bar. Okay, this is the bar and this is the shaft. Okay, let's just compare term by term. The load we apply to bar. What is the load we apply to bar? Simply we apply P. The load we apply to shaft is simply torque T, right? Right?
Yeah.
So load is the, sorry. Load is simply P, right? And shaft load is T. And cross-sectional properties associated with bar is simply A, right? But cross-sectional property associated with the shaft is polar moment of inertia. There's no A here, no A. So remember in the bar you have the dA equal A. In shaft you have R squared dA, which is the IP. When you have an integration, there is nothing there, but here you have a R square, which give us, so cross-sectional property. We can have many different way of defining the property of these cross-sections. We can cross dA, this is simply A, or RdA, or R squared dA, or R third power dA, many terms, right? Which can represent characteristics of these cross-sectional properties. And for the bar, we have the cross-sectional A, area A, and for the shaft, we have the polar moment of inertia. Now, deformation, delta, is simply P times length L and divided by EA. You know that, right? And for this shaft, what is the deformation in a shaft? It's simply rotations. When you have the fixed and you apply rotation, the angle of rotation is simply phi. And here, the deformation is a delta, right? So delta is simply P times L over EA, and phi is torque T times L divided by GIP. And pay attention to each terms. Here is P and T and L, and this is E, Young's modulus, whereas we have shear modulus. And instead of A, we have polar moment of inertia. Why do we have a G? Because it's all shear related deformation, whereas this is all extensions. So material property is E, and this is a G, and stress is simply P over A. The P is the force you apply over the area A, and this is the torque T you apply over the area property IP. And simply this stress is proportional to the R, so we have R here. Okay? And while I know this subject is new to you, but you need to be able to drive this step by step from the very blank. Okay? So I really recommend you to drive this procedure with a blank paper. Keep driving. Okay? Keep driving. And starting from this one, and always displacement, strain, stress, force. Force is a torque here. Displacement, strain, stress, and torque. Actually, same for this bar. Displacement is simply delta equal L times X, and we can do similarly. Okay? Now, that is all about the torsion theory. And now, second subject for the torsion is the hollow thin wall shaft. Hollow, this is the closed. Thin is another keyword, very important keyword. Thin. Thin means that this thickness got to be very thin with respect to other dimensions. Hollow means that we have an empty hole there. And thin and closed. Torsion of a hollow, thin wall, closed shaft. And in this case, it doesn't have to be circular. Okay? Doesn't have to be circular. It can be any shape. Any shape's okay. Like a wing. Always a wing is empty in there, inside. There is some structure which is called shear web. This is called web. Usually shear web. And this is the old skin. This is the typical case for this hollow thin wall shaft. Only difference is that this is the one cell and this is the two cells. We call two cells. How many enclosed the section we have? If we have two webs like that, how many cells do we have? 1, 2, 3 cells. So we call a multicell. Anyhow, let's continue to cover this hollow thin shaft on Thursday. Any question? No. Thank you. And see you. Bye.